you. So we finally finished grading exam 1. The scores have been posted on Canvas. Exams are available for pickup from our TA Jonathan. So if you haven't already picked up, please go ahead, do that. I will upload the exam 1 solution as well as the rubric we used for grading for your reference. Okay. So today I want to continue talking about integration, but in the last 30 minutes, I want to go back to regression. I want to regress back to regression a little bit and do one example that I posted as a participation exercise. Okay. So we'll start with this example. Last lecture, we saw trapezoidal rule for which this is the formula. I want you to get practice. So let's solve this problem with 5 segments. So you're going to divide the interval 0 to pi into 5 segments and obtain the value of I. So let's go. Please consider this like an exam situation and solve this problem using trapezoidal rule. And we'll see one more algorithm called Simpson's rule today, which is similar but also is a little more accurate. So we'll start with this one. Please start. If you don't know how to start, let me know. I'm trying to just set this up in Excel, so I'll have the numbers ready. So if you are doing this in the exam, here's how I would suggest setting it up. Okay. So you have your x and f of x, and you want this to run from f of a to f of b. So a being 0, and that would mean I will substitute 0 here, which will get me this. And then b is pi. For this particular function, sine pi is 0. So this is also 0. So you know that your function will start at 0 and end at 0. But instead of being a regular sign, it's going to be something that is damped heavily by the exponent term. So it's going to look a little different. And then you need to compute these intermediate points. This is where a lot of people don't do this correctly. So what you want to do is understand 5 segments, which means each segment is 1/5 of the range. This is pi over 5, which if you do the number, that's like 0.6283. 0.6283. So generating these values is your first step. Generate 4 or n minus 1 equal to 4 values. That will be 0.6283. Two 564. 64, 1.8850, and 2.5133. B equals pi. You know pi is 3.1416. And then you compute the corresponding x values by substituting in the function. Remember, if it is stated like this x is always in radians. So when you have your calculator setting, make sure it's set in radians. So 0.3961. 0.1961, 0.0273, 0.0272, 0.0011. Okay. So then what I suggest you do is have a weighting factor, WI. For the trapezoidal rule, the first number is just as it is. Everything intermediate is multiplied by 2, and the last number is as it is. So we want to call the weighting factor is 1 for the first and last values of the function, and 2 for everything intermediate. Because this weighting factor will differ for each method. So most of what you learn in this example of generating a number of values, evaluating the function, multiplying by the weighting factor, and then the next column would be Wi times f of xi. So product of these two columns. Seven nine two three. 7923.3922. So this structure won't change. The only thing will change when we do the next method are these weighting factors. Yeah. So the weighting factor is just taking this trapezoidal rule formula and trying to set that, think of it as this is multiplied by 1, while as everything in between is multiplied by 2, and the last number is multiplied by 1. So I'm introducing a weight of 1 and 1 for the first and last, and 2 for everything intermediate. Yes.
The last value of the third column be 0.
This one?
No, in the third one.
Yeah. Oh, 0.
Fourth one.
Yes.
How are you generating the numbers in the xi column?
Good question. So these segments, if I write xi equal to a plus I times delta x. So x1 will be a, the first value, plus 1 times delta x. x2 will be a plus 2 times delta x, where delta x is equal segments That is the range divided by number of segments. Sorry, I might have skipped over that. Thank you for asking. So you want to write down, if you have 5 segments, you know you are going to have n minus 1 intermediate values. So x3, x4, a plus 3 delta x, a plus 4 delta x. Or 4 is nothing but n minus 1. Thank you for asking that. Yeah. Yeah, potato. So what would be the next step? Next step would be to write I equal to 1/2 delta x times I equals 1 to n, summation wi f of xi. That is sum of this column. Sum this column. I mean, in the exam, I wouldn't ask you for an outrageous number, anything more than 4 or 5. But if you are using Excel or MATLAB, you can do like 1,000 values and automate that. But we'll do these 6 values here. Okay, so if you sum that up, I won't tell you. Please do that, and let's make sure we are getting that. So our integral value is going to be half times our delta x value is 6283.6283, and the sum value is 1.2411. Point 3898. Easy enough, right? Like it's just a straightforward application trying to show you the steps. Now comes the question. If you obtain this number in the test, how can you be sure it's correct, or how can you be sure at least it's not absurdly wrong? What are some sanity checks that you can do for an integral that looks like this? Obviously, integrating it directly may not be easy, but what quick tests can you do to check it? If this integral were between 0 to pi, but if it's only sine x, that graph looks like this. Okay, so what's the area under the sine x curve? How to get that? Area under the sine x curve would be 0 to pi sine x dx. And what's the value of that? Minus cos x from 0 to pi, which will give us 2. Right? So what we have here is 0.38. So this is the easy part. That is all. Getting the number is easy, but how do you ensure this number is a reasonable number? Of course, if you have an independent MATLAB or Python program, you can run it and do a cross check. But what logic can you apply with your own brain to ensure that this is a reasonable answer? Can we think of some tests? That is this process, breaking this area. So this is the graph of sin x. Okay, it's not the function that you are seeking. That will have a value of 2. So the first logical test I can pose is any number that you obtain should be smaller in magnitude than 2. If you got a number that's more than 2 due to some algebraic, some silly mistake that you did, off the bat, some red flag should go up because this number has to be less than 2. Why? Has to be less than 2. I'm so sure. Why?
Is the function larger than it? Has an area of 2 and it fits within that area.
Say it again.
Sin x is a larger function, has larger area. It's an easier one that we know. It has to fit within that. So if it is beyond the bounds of that, it's not right.
Right.
Common sense.
The other, and that's correct. The other way of saying that is, if this is my function, I see this number like a damping coefficient. Look at this function. It can never be negative. Its maximum value is 1, which happens at 0. And after that, this function only goes down in magnitude. It's like a damping coefficient. So if this is sin x, what will be the product of sin x and e power minus x squared? How will that look like? It's like at every point, whatever the value of sin is, I'm damping it by this factor. And he said that in words. He said sin x is a curve that bounds our curve. So our curve should be within sin x. So how will you draw our curve? How will you draw this function? Smaller arc of decreasing amplitude. Its amplitude cannot be same as sin x. It cannot be constant.
The amplitude is bound by the e to the negative x squared. So if you can roughly plot that function, you know that it's going to oscillate between the two bounds of both sides.
So e power minus x squared looks something like this. If this is 1, e power minus x squared will fall off precipitously and quickly become 0. So you are getting the product of e power minus x squared and sin x, which means the curve that you are seeking will be something like this. It will die out sooner than sin x because you are damping it by e power minus x squared. Okay, so first sanity check is this number has to be smaller than integral 0 to pi sin x, which is like the upper bound for this integral. What other test can we do? Again, no, we don't want to rely on another software or algorithm. What can we do to check this? Look at this function e power minus x squared. It's 1 or it's non-zero only for small values of x. As soon as you hit larger values of x, this function is practically 0. Okay, so one of the tricks I like to do when I encounter an integral that is not easy to integrate is I try to write it as a series expansion and break it into integrals that I can evaluate pretty easily. So how will you replace e power minus x squared as an infinite series? What's the expansion for Taylor's expansion for that? It's not a trick question. What's the Taylor's expansion for e power minus x squared? What's the Taylor's expansion for e power minus x? E power minus x is 1 minus x plus x squared over 2 factorial minus x cube over 3 factorial plus to the 4th over 4 factorial minus up to infinity. So if I want e power minus x squared, I just have to replace x with x squared. Okay. 1 minus x squared plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 4 factorial, sorry, 2 factorial, 3 factorial, 4 factorial minus and so on up to infinity. With me so far? I'm I know of a numerical method to integrate this. I got the answer. Now I'm trying to see what can I do to verify that answer. With me so far? Yeah. Okay. So then I can say e power minus x squared is approximately equal to 1 minus x squared for small x. Can I say that? For this portion, I'm trying to approximate this as a parabola. I'm not worrying about the higher order terms. I'm just throwing them away. Okay. So if I do that, if I want 0 to pi e power minus x squared sine x, that is approximately 0 to pi 1 minus x squared times sine x dx. That is like 0 to pi sine x dx minus 0 to pi x squared sine x dx. Now I know what you're thinking. I need a numerical method to solve this. That's what you're thinking. Well, kidding. You should be able to solve this using integration by parts. That's the whole process of validation. We don't want to again use a numerical method. So what is this? This is 2. We just did that. 0 to pi x squared sine x dx. So I'm going to evaluate that. 0 to pi x squared sine x dx would be x squared minus cos x from 0 to pi minus or plus 0 to pi 2x cos x dx. This will be minus or pi squared plus 2 times 0 to pi x cos x dx, pi squared plus 2 x sin x 0 to pi minus 0 to pi sin x dx. Let me know if I miss any step in integration by parts. This is pi squared minus 2 pi or pi times pi minus 2. So this is 2 minus pi times pi minus 2. Can you punch this and tell me? Say sine here. Pi times pi minus 2. x times cos x. Oh wait, I made a mistake here. What is integral 0 to pi sin x? Two times. What is this? This is 2. So minus 2. So this is pi squared minus 4. What is pi squared minus 4? Squared minus 4. So this is 6 minus 5 squared. On this. Maybe we still have to include one more term. That it will work out. Okay. I'll get back to you on this. I don't want to get stuck on this. Okay. So we did do one test that it has to be less than 2, which it passes. So what I would like to show you now is how this number gets better as n increases. As n increases, what happens to the value of I? What do you think will happen if we make the number of segments more segments to do the same integration? Sorry?
Less error.
Less error. So if you are done writing this part, I'll pull down the screen and show you an Excel calculation. Okay. Can I bring the screen down? Okay. So please look up. You can continue later. Okay. So here is the problem solved using 5 segments. N equals 5. This is the repeat of what you did. We got 0.3892. Okay. This is what we got with 5 segments. Now, before we do more segments, let's say we do just fewer segments. That is, if we do only 3 segments, the value we get is 0.63. So this is the same problem done using 3 segments or only 2 intermediate values. Okay. So we get 0.63. It gets worse if you do fewer segments, obviously. So if I do, let's say, only one segment, okay, if I just do one segment, sorry. All right, this is with three segments. I'm sorry, the actual value is 0.31441. So I'm going to make a note of that saying number of segments used and the value of the integral that we compute. So when we did 5 segments, we got 0.38. And when we did 3 segments, we got 0.3142. What did we get when we do 5? 3898. 3898. Okay. And if we do only one segment, that is n equals 1, you can see here sorry, n equals 2, that is 2 segments. Okay, the value you get is 0.1332. 0.1332. 3898. 5 segments, 3898. And from 5, I'm going to double the number of segments. So from 5, I'm going to go to 10 segments. Okay, some value here is to be updated. Okay, so for 10 segments, I'm getting 0.4161. Just make sure if I did everything right, 0.4161. So 10 segments, 0.4161. Okay, just making sure everything is right. Let's go back here, do 5 segments. Okay, 0.5 segments. The summation should be up to 3.14. Okay, so 0.3898 and 3 segments, the summation, oh, sorry. So if I do 5 segments, I have to do this. Okay, and if I do 3 segments, I have to do this. I have to sum only up to here. Just making sure before I draw conclusions from there. 0.3141. So we are good up to here. Okay. So let's do 20 segments to see how whether this trend continues or will it terminate at some point. So if we do 20 segments, okay. Getting 0.4224. 20 segments, 0.4224. So take a moment, look at this table. What do you think is happening here? Initially, we went from the minimum number 2 to 3 to 5 up to 20. What's happening to the value of the integral? The slope is decreasing. You can see that, right? Initially from 13 to 31, that's 18 units. 31 to 38, 7 units. Slope has come down already. And then when you double the number of segments, the slope is increasing only by 3 units. And when you double again, it's increasing only by 1 unit. The slope is already approaching 0. we don't know if we are there yet. So what do we do to know if we have reached the optimal number of segments? Double it one more time and see. So we'll do 40 segments. We'll do 40 segments and try to see. Those who have a laptop, you can easily set this up and do with me. So we'll do 40 segments. Okay, and I need to update the summation to go all the way down to Q45. So I'm at 0.4239. 0.424239. So if you see, when you double the number of segments, the increase in slope or increase in value is only 15 or 0.15 in absolute terms. Okay, so we are clearly flatlining here. So then we can continue this. So when do you stop? What's a reasonable convergence criterion for such a thing?
1% error.
So you don't want this to change by more than 1%. 1% is actually too liberal, in the sense too generous. You can go within 0.1% or 0.01%. So you can set your criteria, and we can stop varying n when the gains are smaller than a chosen value, like for example, 0.1%, something like that. Okay. So I'm going to do one more though. I'm going to do up to 80 and still populate a value, because there is still something that we can get out of this. So 80. Okay. So for 80, 85. I'm getting 0.4243. 0.4243. So this is 4 units. This is 0.0004 change. So now we are within 0.1% already, because the change is happening only in the third decimal point. Okay. So with me so far, as we increase number of segments, the value converges rapidly to a number which we can construe to be the value of the interval, or which we can take as the value of the interval. Okay. So here is another exercise we can do. Treat this like your X data, treat this like your Y data, and just for fun's sake, let's try to get what is the trend between I and the number of segments. Can we do that? Like, quick question, this n varies between 2 to 80, whereas I varies between 0.13 to 0.42. Clearly, this is linear, whereas this is logarithmic. So what kind of a fit will you choose for this? Should you try plotting a linear between I and n, or I and log n, or log I and n, or log I and log n? Which choice will you pick? N and I and log n. And can you also tell us the reasoning? So if this is exponential, that is between 2 and 80, there's a huge spread. The logarithm of this will be a linear point. So we are going to plot I and log n, obtain a straight line fit, and you're also going to do some practice on curve fitting through this experiment. Okay. You're not happy about something? No?
Unrelated to this question.
Sorry?
Unrelated to this question. Has nothing to do with you.
All right, so what I'm going to do is to type in n and I as a function of n. So for 2, somebody needs to look over and dictate for me what is the value of I for n equals 2. Okay, 3, 4, 2, 5, 10. Thank you. 20, 40, 80.
0.4243.
Thank you so much. So first thing is, let's visualize it. Okay. Here is our graph. Okay. So here is our graph. Clearly doesn't look linear. What does it look like? Like what curve would you use, or what adjective would you use to describe this variation? I mean, exponent and logarithm are inverse of each other. Since this curve looks like a cliff drawn backward, it's logarithm. Okay. So what we want to do is to plot I versus log n. Okay, log n. So then if we consider this to be x and this to be y, this is log of or ln of n, ln of 2, and then we visualize the graph between I and log n. Okay, this doesn't look like a straight line either. Okay, so we know we have learned one trick so far, which is to fit straight lines. Here's a graph between I and log n. That doesn't look like a straight line. So it's a nice segue for me to do my next thing. So how do you handle this type of situations where the one trick that you know, that is to fit straight line, wouldn't cut it? Do you recognize the problem first? That is, we wanted to see if I plotted against log n would give us a straight line. It didn't. Okay, yes.
We do log I and log n.
Okay, let's try that. So you want to try log of I, right? Log of I. So I'll do natural log of this column. Okay, and we'll make a graph between. Oops. Okay, that is not working either. So if you see here, this is the graph between, this right side is the graph between log I and log n. It won't work. You could have said that from the beginning, because if it's a straight line, it has to continuously increase at some rate. Obviously, this is flatlining, so it won't be a straight line. Okay. So then my question then becomes, how do you handle such curve fitting situations where the straight line is not going to work? We'll answer that. Before that, I need to wrap up this part. So the takeaway for integration from here is, as n increases, the value converges to a particular sorry. As n increases, I converges to the exact value. And in most cases, that exact value cannot be determined straightforward way, because the integration is so hard to do. That's why we resort to numerical method. So in exam, you're going to stick to this 2 to 5 range. The number of segments will be 2 to 5 to keep it manageable. In reality, you want to maximize the number of segments, but how far should you go? Instead of 80, should you keep going, make it 100,000, make it a million? What is a reasonable way to say 80 is good enough? When the gains stop increasing much, you stop. Maybe 100 is good enough. Maybe 1,000 is good enough. So it depends on the function. Some can converge quicker, some converge slowly. But once they converge, you can stop. Okay. So that's the takeaway for integration. You use this trapezoidal rule in exam. Do the asked number of segments. In reality, do a required number of segments for obtaining a reasonable value. Question before we move on? Okay. So, yes. We just did trapezoidal rule. We didn't do any other formula yet.
Yes, but there was this.
But they are equal. They are the same thing written in two ways.
So we should, so in an exam, I should use this one.
Yeah, sure. Okay. This is the participation exercise I posted. For the two lectures I did last week, I wasn't very happy because the linear fitting and quadratic fitting are so doctored, so made fit to a course or an exam that it's practically useless. So I had to go back and think about what will actually be something you will use in real life. And I made up this data set by combining three functions and adding some noise. And then I gave you only this. Okay, I gave you this, which if you plot it will look like this. So how do you set up a regression that will allow you to fit a straight line through this data set? That's my question for you, or that's the question we are posing, and then we'll try to answer it. Okay. So let me open another file here. So this is the file that was given to you, where in the example sheet, I showed all the calculations. I'm going to go over those calculations now. And in the end, I was able to draw a line that ran through the data. Okay. So this is what we call a fit, which functionally replaces the original data. That is, if I provide you the equation for this curve, you can generate this data set. That's the implication. Okay, or you can have all the features that are contained in the data set, including the inflection points, the points where it reaches a peak or reaches a valley. Every little detail must be captured. That's what functionally equivalent means. Okay, before we begin, any question so that we can get some doubts clear? Okay. All right, so the three functions that I use to generate the data, to keep this useful but also not too complicated, I'm going to tell you the three functions, but I won't tell you in what ratio or proportion I combine them for you to get this data. The three functions are exponent of minus x, exponent of minus x over 2, and then sine x. Okay, so I'm telling you that the data can be represented as y of x equal to a1 f of x plus a2 g of x plus a3 h of x, where f of x equal to e power minus x, g of x equal to e power minus x over 2, and h of x equal to sine x. Okay, I'm giving you this. Obviously, there can be more functions, so you can create this or represent this data out of many number of functions or any number of functions. So these A1, A2, A3, A1, A2, A3 are the fit constants that we want to get. You can also call them weights or proportions. And these three functions are called trial functions. Anybody taking finite element method currently or taken it before? So remember this word, this will appear a lot in FEM, where you construct interpolations or representations of each element. They are called trial functions, same idea, okay? So for a quadratic fit, what are the trial functions? Can you quickly think, like generalize this to a quadratic? If f of x equal to 1, g of x equal to x, and h of x equal to x squared, this is the quadratic fit that we learned. Okay. The main requirement for these trial functions is that they all be linearly independent of each other. Now, what do I mean by linearly independent? What is being linearly dependent? What is, when I say two functions are linearly independent, what are we implying? Those who have taken linear algebra or taking, or just from your calculus courses, what is being linearly independent? So y of x equal to a1 f of x plus a2 g of x plus a3 h of x. F of x, g of x, h of x are linearly independent. Okay, what that implies is that g of x by f of x is not some constant always, or h of x by g of x is not some constant always, or f of x by h of x is not some constant always in general. What if it is a constant? What if this ratio is a constant? Or in other words, if let's say f of x is e power minus x and g of x is 3 e power minus x, their ratio f over g is just 1 over 3. So what does that mean? They are linearly dependent because you can express one in terms of the other. It's like saying, this is like saying g of x is not separate, it's just 3 times f of x. They don't have independence. You can't choose them separately. They have the same value, just scaled by a constant. Okay. So the first requirement for these trial functions is that trial functions are or must be linearly independent. That is, if they are trial functions, then their ratio will not be a constant. If their ratio is not a constant, then they are trial functions. So you tell me f equals 1, g equals x, and h equals x squared. Are these three linearly dependent or independent? Dependent? So ratio of 1 is to x is not a constant in general. Ratio of x to x squared, not a constant in general. Ratio of 1 to x squared, not a constant always. So they are linearly independent. So the three functions we have chosen, f equals e power minus x, g equals e power minus x over 2 and h equals sine x. You can check this, they will come out linearly independent. You can never take a ratio of any two and make them to be a constant. Okay, so they are okay. So I have this equation y of x equal to a1 f of x plus a2 g of x plus a3 h of x. With me so far? Yes? Good? Good? Same? Good? Okay. So you have your x data and y data. We'll call it x1, y1, and so on, yn. What is the attribute or requirement of a fit? What do you say a fit must basically do as the first thing?
Represent the real data values.
Represent the data, or whenever you have y of x, okay, this is yi, this is xi, this is the fit. Y of x is similar to yi. That's the first requirement. Or in other words, if you substitute xi here and yi here, this equation must be satisfied. So that's like writing yi equal to a1 f of xi plus a2 g of xi plus a3 h of xi. For any xi and yi. For any xi and yi, this must generally be true. Right? Which means it's true at every point. It's true at every xi, yi point. Okay. What does that mean? If it's true at every data point, I can write n equations for like this. I can write it for 1, 2, 3 up to n, and I can add all of them up. Okay. So we write n equations and add all of them together. So we get sigma yi, where I runs from 1 to n, a1 sigma f of xi, where I runs from 1 to n, plus a2 sigma g of xi plus a3 sigma h of xi. Right? So we get we have gotten one equation for a1, a2, a3. Okay. Now remember what I said about being linearly independent. If they are linearly independent, that is, if this is true, then we can write R f of x and x times f of x linearly independent. What do you think? That is, if you take x times f of x ratio to f of x, this is equal to x. Is this a constant in general. Is this generally a constant? If I just take a function and x times the same function, can I call them linearly independent? Yes, no? No? Why do you say no?
Because X is a variable, still, and they can be.
So you're saying it's not a constant, you're saying no to this question. Right? So this is no, which means yes, they are linearly independent. That is, a function multiplied with x and the function itself are linearly independent. Which means if I take this equation and I multiply both sides by, let's say, xi, I generate one more linearly independent equation. Okay, so that's the logic in multiplying xi. So I have xi yi equal to a1 xi f of xi plus a2 xi g of xi plus a3 xi h of xi, and then sum over all n data points, we get sigma xi yi a1 sigma x f of xi plus a2 x g of xi plus a3 x h of xi. So this is equation number 2. Can you tell me the next step, please? Any of you? I need to generate a third equation. What should I do? Multiply by another xi or x squared, generate a third equation. So I will do sorry. I'll do xi squared yi equal to a1 times xi squared f of xi plus a2 xi squared g of xi plus a3 xi squared h of xi. So I have my third equation. Use any linear equation solver like the MATLAB script I posted to get a1, a2, a3. And this is exactly what I have gone through in that sheet called example. Okay, I'll bring it back here. If you're done writing, let me know. I'll bring back and show you. Can I bring the screen? Yeah. Okay. Can I bring the screen? So please take a pause from writing. Look up, please. So here is the original data. First two columns, x and y. We have the original data. Then I look at my three equations and I recognize all the quantities that have to be computed. I need sigma y, I need sigma xy, and sigma x squared y. So I'll highlight these. I need these three quantities. Okay, so I compute them and I essentially have to do row multiplication, create a value, and then get the sum of each in the top row. So sigma y, sigma xy, sigma x squared y. Okay. Then I need sigma fx, x times fx, and x squared times fx. So I created these quantities because those also appear in my three linear equation. Okay. And then I have g, x times g, and x squared times g. Okay. And then I have h of x times h of x, and then x squared times h of x. So all the terms I need, once I gave you the xy data, you can compute them as secondary quantities, which is what you should do for the data that you are provided as example, or to do, sorry, the exercise is for you to fit this data with trial functions sin x, cos x, and sin 2x. So you have to figure out what a0, a1, a1, a2, a3 are. Okay. So once I have these sums, I have a matrix here. This is essentially the three equations. 386 is the coefficient of A1 plus 97 A2 plus 165 A3 equal to 22.07. So three equations. So from there, I used the MATLAB script to solve for A1, A2, A3. And here are the three values. This is like the weighting factor. So I multiply 0.4142 with e power minus x plus 2.1218 times e power minus x over 2 minus 0.2504 times sine x, and that should give me my data. Does it? I check that by computing y fit. So you can see here, y fit uses these three numbers and those three functions to recalculate the fit value. And I compute the quantities. And if you see here, the blue data points are the original data. The dark line is the fit. Okay. You should produce a similar fit for this function or this data set. That's your participation exercise. You do this, create this Excel file or update this sheet. Each of you do this independently and upload your submission. Got it? Okay. Now real life gets more interesting. This is still a very doctored problem where I gave you a trial function. I told you what the trial function is. In real life, you will only be presented with data. No, most cases, nobody is going to tell you what the trial function will be. So you have to try different things and develop intuition and be able to say what function will fit these given data set. That's one. The other simplification I did, anybody, can you recognize what other simplification I've made for you? What one simplification, if I didn't do, this would be much more or a nonlinear problem. No, that can still, you will get a poor fit, but it's still not impossible. There is one more simplification I did, which if in real life it may not be the case. So what else can be difficult here? Think about this three trial functions. I gave you e power minus x, e power minus x over 2, and then sine x. Think about those three functions. What about that function sticks out to you? They are linearly independent. If they are not, we can't use them. So at this, if you are this far, we assume that you will select only linearly independent functions. So that's not the simplification. Why e power minus x? Why not e power minus 0.9x? Why e power minus x over 2? Why not e power minus x over 4? Why am I giving you very specifically that function? If I didn't tell you that, but I just told you, hey, it's some kind of exponent, what would you do? You'll say it's like e power minus alpha times x, where you don't know alpha, and alpha has to come from your fitting. So that one step will make this a nonlinear problem. Instead of this, so you see this equation here, right? Notice that A1 contains all of the fitting information, and f of xi depends only on x data. It doesn't care about any other fit constant. But what if I say one of the trial functions, instead of being e power minus x, I'll say e power minus alpha x. Then you will get e power minus alpha xi. So this whole equation, wherever you have f of x, it will be replaced by e power minus alpha xi, which makes this problem into a nonlinear problem. So the biggest, whenever, especially in this project, some of you may encounter this, your data may not readily be amenable for a very simple trial function, and you may have more fit constants even within your trial function that could make this thing nonlinear. But we are not doing that. Okay? I gave you a simplified set of trial functions here. Okay. So coming back, okay. So you calculate the fit, all right, and you should be able to say the fit captures all the features, all the geometric features seen in the data. With me so far? Yes. Okay. Now comes the question: what is the confidence interval on this fit? Like, how good is this fit? Will it have a wider band around it or a narrower band? How do we quantify that? So we talked about this also in the context of quadratic and linear fitting. So in the sheet, I have given you how to calculate that. So please focus on these two columns. What is this? Y data minus Y fit. Difference between columns X and Y. What's the attribute of a good fit? It should minimize that difference. That number in column AB should ideally be 0. That's the attribute of a good fit, or should be as small as possible. So you take the difference, you take the square of the difference, which means you're taking essentially the magnitude, and you sum everything, and that is what we see here. Sum of the difference squared. Sum of the difference squared, that is this column here. Okay. So if this everything were 0, you will get a sum that is 0, but we are getting some finite value, obviously. And this here, this row is degrees of freedom. What did I tell you is degrees of freedom? Do you recall? If you are compressing n data points into a fit that has, let's say, 3 fit constants, what is the degrees of freedom? N minus number of fit constants, or in this case, n minus 3. So we have 351 data points. So if you look here, the degrees of freedom is calculated as number of data points minus fit constants, which is 351 minus 3, or 348. 348. Okay. So the standard error is square root. Standard error we saw previously. Standard error estimate is yi minus y fit squared divided by degrees of freedom summation. Okay, so that is SE, standard error estimate. With me so far? I mean, this whole thing is not a lot of concepts. It's just a bunch of steps that you have to do in sequence. Okay, so stick with me. And what I'm doing here is for 348 data points and at 95% confidence level, I'm getting t-value, which will obviously be like 1.96 because it's a large number. It's already approached the standard normal distribution. So this is t-value. And then number of observations. So confidence interval, if you recall, confidence interval is t statistic multiplied by the standard error estimate divided by square root of n. So your confidence interval for the fit is calculated over here. Okay. So this number Ci, it's like an upper bound and lower bound on the prediction you get from your fitting. So you calculate y minus Ci and y plus Ci, and you can get two sets of bounds, lower and upper, above your fit line. Okay. So this is what you are expected to be aware of and implement that for this particular problem where you are going to work with sin x, cos x, and sin 2x as your trial functions. Okay. So if you need help, if you just go back to the example, you should get most of it, but you can actually come and ask me. Yes.
So the p-value times SE.
T-value multiplied by SE divided by square root of number of observations. Okay. Other questions? Okay. All right. We have 5 minutes. I want to do something else here. Okay. So look at this data. We did curve fitting so far. Okay. Now, if I ask you for area under this curve, how can we do that? Think about it. Let's not go for the route where you first fit a function, you know the function, and then you do integration of that function. Let's not do that. How can we compute area under the curve for a data set for which you don't know the function, for which you don't want to compute functions or fit a function? You just got a table of data. How will you compute area under the curve for 0 to 3.5?
You do the delta y between the function and 0, and you sum across that.
I think what you mean is treat every value of y, treat every value of y like f of x, and essentially apply trapezoid rule with a step length of 0.01 or the resolution of the data. Okay, can we do that? If you have your laptop, this file is online. You could have downloaded that, or you could do it now, or you could watch me do this. I'm going to add a weighting factor, w of x. For the first data point, it's 1. For the second data point, it's 2, and it's 2 until the penultimate data point. And for the last point, it's 1. So then I'm going to write wx times y. Okay. And that is just the product of these two columns. Okay. And then I want to do sum. Sum is sum of this column. And what is my I? I is half times step length. So step length I could have just figured out from here. That's essentially the difference between x second value and first value. So this is half times delta x times summation. Oh, I'm still missing something. Divided by number of observations. How many data points do I have? I should check that, or I have n data points, which I know is count of this, which is 351. I know that. If I have 351 data points, how many segments do I have? So I have A, B, A is 0, B is something like 3.5, I think, something. And then I have x1, x2, and so on. Counting this and this, I have 351. So how many segments do I have according to our formula? Number of segments. 350. Yeah, I think so. 351, which will mean 349, 350. Yep. So that is like n minus 2 plus 1, 350 segments. Okay. The step length already includes the number of segments, so that's good. We don't have to do it again. So half times step length multiplied by the sum. So that gets me 3.85. Okay, 3.85. With me so far? 3 more minutes. This data doesn't look very smooth. There are lots of ups and downs. So one trapezoid can be something. The next trapezoid is not uniformly increasing. It could also be smaller because the data is very noisy. Do you recognize that? What do you do with noisy data? Or in other words, this 3.85 has, in a sense, it has information about this segment, which is largely the area you're seeking, but it also has some noise. So how do we kick out the noise from this calculation? What do you do? What can you do about noise? No fit. We are taking off that option off the table. What else can we do about noise?
Like I'm thinking about Chauvinet's theorem where you could throw out certain points that are out like outliers per se. And then you could just do what we just did over the non-points.
If you do Chauvinet's theorem or outlier rejection, none of those points will qualify as outliers because they are noise which are mostly closer to the baseline. They are not out there. They are actually pretty much following the mean. They won't be ever classified as outliers. So that won't work. What else can you do? Yes, Daniel, please say that. Don't mouth it. Thank you. Please say that loud and clear. Yeah.
You can take just averages.
What do you mean by average it out? I agree with what you are saying we should do, but what is the logic behind that? What he's saying is he wants to take this curve or this data set and make it smooth. And I'm trying to ask him based on what criteria should we smoothen it? How do you smoothen it? On what logic? We are going to pick this up next class. So first question, we are going to come back here and ask how do we smoothen it. So this is going to be like a participation thing for next lecture or the following lecture. Okay. But for today, please please do this. You have 1 week to do this and upload it by next Tuesday. Okay. Thank you.